Welcome back to Hardware Unboxed. Today is the day we can finally talk to you about AMD's FidelityFX Super Resolution, or FSR technology. Make no mistake, this is AMD's competitor to Nvidia's DLSS, a feature that has increasingly become a key selling point for GeForce graphics cards in the last 18 months. It's taken AMD a long time to prepare their own upscaling feature, but from today, AMD are ready to compete. This video is going to be a comprehensive overview of FSR. We've got a stack of quality comparisons at different resolutions, performance benchmarks across several GPUs, and comparisons to other upscaling technologies. So sit back and relax as we take you through everything. There is a lot to cover.
Today's video sponsor is Gigabyte and their brand new range of Intel 11th generation hardware. Gigabyte offers an excellent range of Intel Z590 desktop motherboards equipped with robust VRM designs capable of extracting the most from Intel's latest Core i9 processors. Then for mobile users, the Aero 15 is a beast, packing a 4K OLED display with HDMI 2.1 and can be configured with either an 11th gen Core i7 or Core i9 processor. So, for more information, please check the link in the video description.
So what is FSR? Well, like DLSS and checkerboard rendering, FSR is an upscaling technology that is designed to improve the performance of games at minimal loss to visual quality. The idea being you reduce the game's render resolution and then use an algorithm to upscale the image to your target resolution, typically the native res of your monitor. Reducing the render resolution improves performance substantially, and if the upscaling technique is good enough, this can be achieved while preserving image detail. The most prominent form of this today is DLSS, which is Nvidia's proprietary AI-based temporal upscaling solution that only runs on GeForce RTX GPUs. Temporal upscaling means data is accumulated from multiple frames and combined into the final image, with the AI component running on Nvidia's Tensor cores to assist with this reconstruction. DLSS has gone through several iterations, but right now we are at version 2, a major improvement over the initial release, which was a bit of a fail. FSR takes a different approach. Rather than using temporal upscaling, FSR relies exclusively on spatial upscaling, and AMD tells us that AI has not been used at any stage of the FSR process, so FSR is not the technology described in that patent that has been floating around. This greatly simplifies the algorithm. Spatial upscaling does not rely on data from multiple frames or motion vectors, which makes it easier to integrate into games as there are less data inputs. However, with less data to work with, spatial upscaling algorithms need to be really good at figuring out how to reconstruct the image, and traditionally this is where they have fallen short. AMD didn't go into detail on specifically how their algorithm works, but this is not simply a rehash of bilinear upscaling, which is the sort of standard method for spatial upscaling today. AMD are calling their technique an advanced edge reconstruction algorithm, which is combined with a sharpening pass to create the final image. And there is only one input to the algorithm, which is the lower resolution frame. Despite being a simpler technique, FSR still requires game integration. This is because FSR needs to be run before the final effects stage in the pipeline, so before the HUD is rendered and before things like film grain are implemented. If FSR was applied to the final frame output from a game, then things like the HUD would be upscaled, likely with artifacts. Doing it this way ensures only the game is run at a reduced render resolution, so FSR only has to upscale the game graphics, not the HUD and other elements. AMD have taken the approach of spatial upscaling for two reasons. The first is, as we mentioned earlier, is ease of integration. FSR is a single compute shader with simple data inputs and is open source technology, which should lower the amount of game development resources needed to implement. The second is that by not using AI, AMD has been able to achieve broader support. FSR works on AMD GPUs from the RX 480 era and newer, as well as Nvidia GPUs from the GeForce 10 series and newer. We can already see this is broader support than DLSS, as it runs on Nvidia GPUs that don't have tensor cores, in particular popular mainstream models like the GTX 1060 and GTX 1660. Now, some people will compare the way FSR works to the way DLSS works and conclude that FSR is not an actual competitor to DLSS because they work in fundamentally different ways. But in my opinion, that is not true. Both technologies are designed to achieve the same end goal: improved performance from rendering a game at a lower resolution, but at a minimal quality loss through upscaling. So it's only fair to directly compare them, and we will be doing that later in today's video. FSR itself has 4 quality modes from ultra quality to performance. Each has a distinct scale factor, 1.3 times for ultra quality, 1.5 times for quality, 1.7 times for balanced, and 2.0 times for performance. What this means is that at a target resolution of 4K, the quality mode runs at 1440p and the performance mode at 1080p with the other modes in between. But FSR supports any resolution, it's not just restricted to 4K and 1440p, and the scale factors will apply in the same way. FSR also works with dynamic resolution scaling and theoretically allows for any scale factor, but for now AMD are trying to keep it simple with 4 fixed modes. Before we get into testing, a quick look at game support. FSR is launching today with support in 7 games, however by my count only 4 of these games are actually released as a final version, the bigger names being Godfall and Anno 1800. AMD also has promised support in other titles coming soon, including Far Cry 6, Resident Evil Village, Dota 2 and Baldur's Gate 3 are some of the more recognizable names. Necromunda Hired Gun will also be an interesting one as that game already supports DLSS, so it might be our first true DLSS versus FSR comparison. But at the end of the day, this support list is just a promise right now. Nvidia provided something similar when they launched DLSS, only for many of those games to never support DLSS, so let's hope AMD doesn't do the same thing. They also showed this slide which has all the studios working to integrate FSR, which includes names like EA, Obsidian, Crystal Dynamics, Ubisoft, Capcom, Unity, among many others. For the upcoming section on quality comparison, all image captures were taken on an AMD Radeon RX 6800 XT using a new FSR supporting driver, although AMD tells us that no part of the FSR pipeline actually sits within the driver, so the driver shouldn't make too much of a difference to quality. Our test system has a Ryzen 7 5800X inside, along with 16GB of DDR4 3200 memory. First up, let's look at how FSR holds up with a target resolution of 4K. This is Godfall running epic settings and no ray tracing or motion blur. It also has sharpening disabled, as we noticed you can sharpen the native image but can't sharpen the FSR image, might be a bug, and we're only interested in native versus FSR, not native plus sharpening versus FSR. This is the very opening scene of the game, and to be honest, FSR holds up quite well when using either the ultra quality or quality modes. Without zooming in, these 3 modes all look pretty similar, and in the game itself, I found it pretty hard to tell the difference. As you move down to quality, there is some softness introduced, but it holds up well, even for elements like foliage. Zooming into the armor area of the main character does reveal a slight quality loss to the highly detailed leg armor, but other areas look virtually indistinguishable from native, especially at ultra quality. The modes that don't look as good, however, are the balanced and performance modes. Balance is a clear step down from quality, and performance is blurry, not the image quality you'd expect from native 4K. I was quite impressed with FSR's ability to preserve fine detail. Here is a scene that shows a spectacular floor detail with lots of fine texture elements. Even when zoomed in, the ultra quality and quality modes are very close to native, and it's only below this where image quality is more noticeably impacted. It's a similar story on the other side of the image with a pile of coins. Image quality holds up surprisingly well for a spatial upscaling technique down to the quality mode, which is rendering at 1440p. Image quality also holds up well in a game like Anno 1800, which is another title that has a lot of fine detail in its native presentation, nice and sharp overall. Now, I'm no Anno expert, so this is a noob level map I have here, but again, between native rendering at 4K and the 2 highest FSR modes, I found it difficult to spot the differences in static images and even more difficult in gameplay. I can zoom in and find areas where there is additional fine detail in the 4K image versus the FSR image, and a small amount of additional shimmering in areas like foliage, but overall, I was impressed with how FSR handles upscaling in a title like this. Of course, everything we have shown up until this point is static imagery, so how does FSR handle motion? Again, I was surprised with the results, which are, in general, pretty good at 4K. In this side-by-side comparison in Godfall, the ultra quality mode does see some slight blurriness in the rock texture compared to the native image, but this blurriness isn't present in other areas. It depends on exactly where you are looking. Quality mode is a bit softer again, but to be honest, in general gameplay, it's pretty hard to spot the difference unless you are specifically doing side-by-side comparisons or looking closely. Where image quality falls away is with the balanced and performance modes. Balance is noticeably blurry in motion and doesn't handle elements like foliage as well as the higher quality modes, while the performance mode is quite noticeable that you're not playing at 4K. If you are at all concerned with image quality, there is no way you'd play using the performance mode. I'd turn down other image quality settings to improve frame rate before using FSR performance, as it's basically a blur filter. One final thing to note is around image stability. Generally, FSR will preserve whatever level of image stability is present in the native image. So if there's a little bit of flickering or shimmering in that native image, that too will be present in the FSR image. You'll see in this scene that as we move down the quality modes, FSR actually amplifies this instability from only a tiny shimmer at native rendering to slightly noticeable shimmer in the quality mode to noticeable shimmering in addition to overall quality loss in the performance mode. It's up to developers to ensure that the image they are feeding into FSR is free of artifacts. Generally, FSR won't introduce motion artifacts as it's not a temporal upscaler. I didn't see things like ghosting across the games I tested, but it can make existing artifacts more noticeable. As AMD told us, FSR doesn't replace anti-aliasing, it's designed to work in conjunction with the game's anti-aliasing implementation. Moving on to 1440p image quality now. Of course, this footage has been upscaled to 4K in this video as it's a 4K video, but my thoughts on 1440p are based on playing the game on a native 1440p monitor. As you might expect, FSR isn't quite as good at this lower resolution, and there's a narrower range of quality modes which are usable in my opinion. In this scene, there are only small differences between the 1440p native image and 1440p using FSR in its ultra quality mode. But as we move down to the quality mode, the image becomes softer and areas such as the character's cape are a bit blurry compared to native. Then similar to at 4K, when we use the balanced or performance modes, image quality falls away substantially and is quite blurry, especially in the performance mode. FSR is simply not very good at upscaling a 720p image to 1440p and retaining the clarity of the native presentation. If we return to this scene we used for the 4K comparison showing a high detail flaw in Godfall, again image quality holds up when using the ultra quality mode at 1440p. However, it is noticeably softer in the ultra mode and falls away from there, pretty similar to what we saw in that previous scene. Very similar situation in this scene from Anno 1800, the ultra quality mode is able to do a pretty good job of upscaling the image from slightly above 1080p to 1440p while maintaining a largely crisp presentation with only slight reductions in fine detail. But when dropping down to quality or balanced, I found it much easier to spot the effects of the lower render resolution, and in my opinion, I wouldn't use these modes. Here is a quick look at Terminator resistance at 1440p, which in general has a softer native presentation. In some areas here, the ultra quality FSR mode looks a bit better than the native presentation as the sharpening pass appears to produce a clearer image. However, it does come at the cost of some temporal stability in areas like the window frame. The quality mode is, however, a reduction in detail compared to native, and the two lower modes are blurry. In our Godfall motion test at 1440p, FSR is pretty similar to what we described in the 4K section. 1440p native versus 1440p ultra quality FSR shows that the FSR image is slightly blurrier in motion, but it depends on the exact area you are looking at as more detail is retained on the door than on the rocks. While actually playing the game at 1440p, I felt the FSR ultra quality mode was that little bit less sharp than native, more in line with the 4K quality mode. This is also why I feel anything below ultra quality is a more substantial decrease to image quality at this target resolution. Again, in this Godfall foliage test, I feel that 1440p ultra quality gets pretty close to the native presentation, but you begin to see the effects of the lower render resolution in the quality mode where some of the moving leaves are blurrier and less defined. At 1080p, FSR is not amazing. Even using the ultra quality mode, there is a noticeable loss to detail compared to the native presentation. In this Godfall detail test, you'll notice shimmering in the character's hair even in the ultra quality mode, which was not true when using the same mode at higher resolutions. There is simply not enough information in a single sub 1080p image to properly reconstruct this to 1080p without quality loss. Anno 1800 has generally been a really good test for FSR and plays nicely with the technology. However, at 1080p, even here the flaws appear. The overall image in the ultra quality mode is softer, the grass, foliage and buildings are all blurrier, so the overall detail level is unimpressive. It gets less defined at lower FSR quality modes to the point where the performance mode is really pretty terrible. In motion, again, the results aren't amazing. The ultra quality mode is probably playable at a pinch, but it's something I'd only resort to after reducing other quality settings or if you have poor eyesight. With the other modes, it's very obvious the game is being rendered below 1080p. I mean, the quality mode is rendering at just 720p, which simply is not sufficient for this feature. In fact, here is some gameplay using the 1080p performance mode in Godfall. This is really not very good quality, and I can't imagine anyone would want to play the game like this in what is essentially the worst case scenario for FSR. Now it's time to talk performance. We had a few choices on how to test FSR performance based on the amount of time we had with the technology, and we decided to stick with testing one game across 8 GPUs using 3 resolutions and all 4 FSR modes. We could have tested more than just Godfall, but the other games AMD provided were a lot more difficult to benchmark, not great for testing GPU limited features, and if we had tested them we wouldn't be able to have done as comprehensive a visual analysis. As mentioned earlier, our test system had a Ryzen 7 5800X and 16GB of DDR4 3200CL16 memory in a dual-channel single-rank configuration, so a pretty typical gaming build. Godfall was tested using epic settings, no additional sharpening, no ray tracing, and no motion blur unless otherwise specified. I don't think the ray tracing implementation in Godfall is worth enabling, so I didn't for this test. Using the Radeon RX 6800 XT, the performance uplift provided at 4K is impressive. Moving from native to ultra quality FSR took the frame rate to 100 FPS, a 44% improvement. The quality mode is also usable at this resolution and saw a 65% uplift over native. The lower modes improve on this again, but don't really deliver 4K image quality, so they're not going to be a big focus of this performance section, but of course you can see the data here anyway. At 1440p, we are more likely to be CPU limited on such a powerful GPU, especially as we lower the render resolution. However, despite this, moving from 1440p native to ultra quality FSR still provided a 25% performance improvement at a minimal impact to visual quality. The quality mode approaches a 40% increase, but I wouldn't recommend using it. Interestingly, here we also get to see the overhead that FSR requires, given the 4K quality mode renders at the same resolution as 1440p native. With this RDNA 2 GPU, we see an 8% reduction in frame rate compared to native rendering, which is not nothing, but in the grand scheme of things, this is pretty small for something run on the same shader units as the game itself. The Radeon RX 5700 XT benefits in a similar way to the 6800 XT. At 4K, I achieved a 41% uplift over native using the ultra quality mode and 66% improvement using the quality mode. The quality mode here basically makes the 5700 XT a 4K capable GPU in this game, as performance rises from a hard to play 35 FPS to nearly 60 FPS. The 5700 XT also benefits more at 1440p, with a 29% uplift going from native rendering to FSR ultra quality. Vega 64 is the next AMD GPU we have for testing using a prior generation architecture. At 4K, we see a 39% performance improvement for the ultra quality mode and 60% for quality. Then at 1440p, Vega 64 benefited to a lesser extent than prior GPUs with just a 20% uplift for the ultra quality mode. This appears to be down to a higher performance overhead on this older architecture, a 10% reduction in frame rate comparing 4K quality to 1440p native, higher than the 8% on RDNA 2. With the RX 570 4GB, Godfall really doesn't play well at all unless we use medium settings, as the game basically requires a lot more than 4GB of VRAM in all conditions on higher settings. FSR doesn't solve VRAM limitations to that degree, but using medium settings, I saw a substantial benefit from switching from 1440p native to 1440p ultra quality, a 47% uplift, which takes this GPU out of the unplayable zone at this resolution. Of course, FSR is also supported on Nvidia GPUs, so let's test that out. The RTX 3080 is more prone to being CPU limited as we lower the resolution and isn't as powerful as the RX 6800 XT at lower resolutions. This is why we only saw a minimal 14% performance uplift at 1440p. We're basically rendering at 1080p here with the GPU being limited. At 4K, the performance uplift was more in line with the 6800 XT, but to a lesser extent. The ultra quality mode provided a 34% increase to frame rate compared to 44% on the 6800 XT. Quality provided a 53% uplift compared to 65% on AMD's equivalent GPU. These numbers are nothing to scoff at though for 4K gamers after a performance boost at minimal image quality impact. The RTX 2070 plays very nicely with FSR. At 4K, we saw a 46 and 74% performance increase for the ultra quality and quality modes respectively. These are some of the highest results yet, and it seems that FSR is able to increase your frame rate more the lower the native frame rate is. At 1440p, we saw a 30% performance boost using FSR ultra quality, which is similar to the 5700 XT at this resolution. The performance overhead on this Nvidia GPU is in line with the overhead on AMD RDNA 2 GPUs, so it doesn't look like this feature has been written in a specific way to hurt performance on Nvidia GPUs. With the GTX 1660 Super, you can expect huge performance uplifts from FSR at certain resolutions, given the card isn't as powerful as some of the others we've been testing. At 4K, I saw a 59% performance increase moving from 4K native to ultra quality, and nearly double the performance using the quality mode. Meanwhile, at 1440p, the 1660 Super also benefited from 33% higher performance, going from native to ultra quality FSR. Then with the Pascal-based GTX 1070 Ti, the performance story is very similar to the previous 8 GPUs tested. A 52% and 82% performance increase for ultra quality and quality at 4K respectively, with a 29% increase at 1440p ultra quality. This makes the 1070 Ti a much more playable GPU at both resolutions, and while I probably wouldn't use this card at 4K in this game, the gains at 1440p are very decent for improving the smoothness of gameplay. The next section of this video is mostly concerned with comparing FSR to other upscaling techniques. The first candidate is DLSS 1.0, and simply put, if you thought FSR was going to be similar to DLSS 1.0 or worse, then you were wrong. Here is a refresher on what DLSS 1.0 looked like in Battlefield 5, which as you can see is very blurry compared to the native image. You need to be running FSR in the performance mode to achieve similar image quality. The higher quality modes are simply a lot better. Titles like Metro Exodus weren't as blurry, but did odd things like change the way the game looked. Take this tree for example, which had nice fine branch detail in the native presentation. DLSS 1.0 changed this tree to look like a thick, chunky, weird looking thing. There is no aliasing here, but there is a big loss in detail. FSR doesn't do this or have any similar issues with rendering. I'm not going to bother showing any more comparisons as DLSS 1.0 is dead at this point, but simply put, FSR easily outperforms Nvidia's first generation upscaler. I would actually consider using FSR, unlike with DLSS 1.0. Next up, we have FSR versus traditional upscaling, and here I'm comparing 4K FSR quality to native 1440p upscale to 4K, noting that both of these modes render the game at 1440p. It's very quickly apparent that the 1440p upscaled image is inferior, and quite substantially inferior, with less detail and more blur. This isn't a big surprise. It would be quite a fail if FSR only matched normal upscaling, but this is confirmation that FSR is going beyond what we already have. The more interesting question is, has AMD faked FSR through sharpening filters? We knew from previous testing that rendering at a lower resolution and then sharpening it can replicate the effect of a higher resolution to some degree, though usually it's insufficient. Here we have the game's built-in FidelityFX CAS sharpening filter applied to the 1440p image, and this is clearly worse than FSR. This has all the hallmarks of an over-sharpened image. In these rocks, for example, the sharpening filter isn't really restoring detail, it's just heightening the differences between light and dark areas. So the game's built-in tool is worse than FSR. But I've gone beyond that to use the best sharpening tools available in Adobe Premiere to see if I can replicate the effect of FSR. Now, these sharpening filters are not designed to be used for real-time game rendering and so don't have an optimized overhead, but typically they work somewhat better than AMD's CAS. Across the space of an hour tinkering with different filters, different parameters and so on, I was unable to match the image quality of FSR's quality mode, which ultimately got the closest to the native image of anything I tried. Now granted, I was able to get pretty close to FSR using this technique, but not close enough. The main issue with using these filters is that when I was able to, say, match the clarity of detail on the rocks, I was introducing jagged edges like bad quality anti-aliasing on the moving foliage and reducing the quality of other fine details. When I matched the quality of the foliage, other parts of the image were too soft. Basically, AMD are doing something in addition to just sharpening the image to get the level of detail seen with FSR. I'm not quite sure how their upscaling technique works, but it does appear to be enhancing the image beyond traditional methods, which is good to see. Of course, the big question mark is how does FSR compare to DLSS 2.0, and I'm sure that's what a lot of people wanted to know heading into this video. This is a very complicated topic, more complicated than I was expecting, because the answer isn't a simple DLSS is better or FSR is better, it really depends. For this video, I took some captures using the latest games and best implementations of DLSS 2.0 that I've seen, in games that also have great native image quality, so no bad TAA games allowed. Cyberpunk 2077 is one great example, and in this game at 4K, DLSS 2.0 looks excellent, with only a very slight quality loss between 4K native and 4K quality modes. The level of detail preserved here in this scene is slightly better than what I observed in the best cases for FSR, but flicking back to Godfall with FSR for a moment, it gets pretty close in a best versus best comparison. Ideally, we'd be able to use the same game to compare DLSS versus FSR, but that's not possible right now. Hopefully at some point in the future we can get to that. Again, at 1440p in Cyberpunk, DLSS 2.0 quality mode is softer than the native image, which is what I experienced in my playthrough, but holds up pretty well and still provides decent detail. I would say DLSS in this situation is again slightly better than FSR using the ultra quality mode at 1440p. One thing DLSS is able to do that FSR can't do is preserve thin line detail. For example, here in Watch Dogs, this thin lamp detail is kept intact with DLSS 2.0, whereas based on what I've seen, I'd expect some quality loss in a similar situation with FSR. Where DLSS 2.0 is clearly superior is in the lower quality modes that reconstruct the image from a lower render resolution. This is 4K native versus 4K performance in Watch Dogs Legion, and yeah, the performance image isn't as good. There's noticeable artifacting on the back of the character's jacket, for example, but overall detail is reasonably good. If we check in with FSR and Godfall, the 4K performance mode is noticeably blurrier when upscaling from the same 1080p base resolution as DLSS 2.0 was using. Similar situation at 1440p in a game like Rainbow Six Siege. There is a loss in detail and quality moving from the native image to DLSS quality, but the loss from quality to performance is reasonably small. Contrast that to FSR in Anno 1800, and the loss from native to FSR ultra quality is small, but ultra quality to performance, and yeah, there is now blur introduced, and that isn't as much of an issue with DLSS 2.0. So basically, for static imagery, in this non-ideal test across different games, DLSS 2.0 appears slightly better than FSR in a best versus best comparison. In some cases, both techniques are able to produce essentially native image quality. In other cases, DLSS 2.0 can preserve slightly more detail. But best versus best is pretty close in my opinion at a similar performance uplift. 4K FSR ultra quality versus native was about 30 to 50% faster, which is similar to DLSS 2.0 quality versus native at 4K in the games we've tested. An interesting note here is that DLSS quality actually uses a lower render resolution than FSR ultra quality, but it does seem that FSR has a lower performance overhead to upscale the image. So FSR is able to utilize higher render resolutions and deliver similar performance to DLSS 2.0. Again, this is not a direct comparison in the same game, so we'll have to explore that further when we get ideal conditions. On the other hand, DLSS 2.0 is superior at upscaling from low render resolutions relative to the output resolution. That's simply because DLSS 2.0, being a temporal upscaling solution, has access to more data inputs, including previously rendered frames and motion vectors, along with some AI magic. How much influence the AI element actually has compared to just having more data points, I'm not sure, but usually with these things, more data in equals better results. So when FSR only has, say, a 2 million pixel 1080p image and needs to upscale that to 4K's 8.3 million pixels, DLSS 2.0 is not only utilizing that 2 million pixel image, but 8 million pixels from the previous frame and other data. This advantage is reduced when the gap between render and output resolution is smaller, because in those instances, it seems that FSR has enough data to produce a good image. In motion, it's a real toss-up between DLSS 2.0 and FSR. Both techniques lose image quality in motion, generally speaking, so the game will get blurrier to some degree as you move around, and usually the amount of blur is relative to the quality mode you've selected. I'd say DLSS and FSR are pretty similar in that area. Both also have artifacts in motion, but differ in those artifacts. FSR tends to have shimmering, which is barely noticeable in the ultra quality and quality modes, but is more apparent in balanced and performance. FSR is also unable to clean up motion artifacts, so whatever the game has natively, FSR will also have. DLSS 2.0 suffers less from shimmering and can, in some instances, clean up residual shimmering or aliasing effects. However, DLSS has its own set of issues. DLSS can cause ghosting, which is not possible with FSR. This is an example in Cyberpunk 2077 where there is noticeable ghosting behind this fast-moving car using the game's built-in DLSS option. Some users have discovered that swapping out the DLSS DLL file with the new DLSS 2.2 version from Rainbow Six Siege can minimize these artifacts, but it doesn't fully remove them, as seen in this footage. I'm yet to spot DLSS 2.2 improve static image quality outside of this artifact reduction. And I should note here that in games that use TAA in addition to FSR, it is possible to have some ghosting, but that's not due to enabling FSR itself. As I said, FSR just continues to use whatever artifacts are already present in the native image, so if that game's TAA has motion artifacts, then those are also going to be present in FSR. But FSR isn't going to introduce new artifacts in the way that DLSS does in some of those situations. I've also just seen other weird stuff from time to time, like this shimmering in Watch Dogs Legion using the 1440p quality mode. DLSS just really seems to struggle with this detail in motion. I've also spotted moire patterns from time to time after DLSS reconstructs an image, particularly at lower quality modes like performance. Basically, when you're attempting to reconstruct a moving image from lower resolution sources, both DLSS and FSR will have artifacts to some degree. They just differ in how those artifacts present in games. So if anyone says, DLSS has no artifacts or FSR has no artifacts, that is definitely not true. There are artifacts in both techniques. Okay, well, that has been a lot of testing. Time to give my final thoughts on AMD's FidelityFX super resolution technology. I have to say that I was a bit surprised with what AMD has been able to achieve with FSR. Back when they announced FSR and how it works, I was expecting it to be okay, but not overly impressive, ultimately falling between DLSS 1.0 and 2.0 in quality. But the reality is FSR is pretty decent in some circumstances and is competitive with DLSS 2.0 at times. For people wanting to use FSR, my recommendations are straightforward. At 4K, both the ultra quality and quality modes get pretty close to native rendering, while delivering around a 40% performance uplift in the case of ultra quality and over 65% for ultra, across a range of GPUs from both AMD and Nvidia. I think most gamers will gladly take this sort of performance uplift for the relatively minor impact of visual quality that FSR has in most circumstances. FSR is also usable at 1440p using the ultra quality mode. Here image quality is again pretty good and gets close to native, and provided that you aren't going to be CPU limited when lowering the render resolution, I was able to typically achieve around a 30% performance improvement in Godfall. The other modes I don't think are particularly usable. The balanced and performance modes suffer from a noticeable quality loss and introduction of artifacts like shimmering regardless of the resolution. And at 1080p, FSR doesn't really cut it, with even the ultra quality mode seeing a loss to image quality. With that said, FSR is better than traditional upscaling, so I could see these modes that do impact quality being useful for APU type hardware, where it might be a choice between rendering at say 720p low settings or 1080p low settings through FSR. In that case, it is better than nothing. I was happy to verify that FSR isn't just the same as traditional upscaling techniques or upscaling plus sharpening. This is better than what we've had previously, giving us currently the best spatial upscaling technique that I've seen. By extension, this makes it better than DLSS 1.0. This is far from a blurry mess in the best quality modes and has lower performance overhead. The battle between FSR and DLSS 2.0 is more complicated. In the best cases, FSR is pretty competitive with DLSS 2.0, although granted we aren't able to compare both in the same game just yet. However, based on my extensive testing and retesting of these techniques, in the higher quality modes, the image quality FSR offers is only marginally behind DLSS while providing a similar performance uplift. It also doesn't suffer from ghosting in motion, as FSR is not a temporal solution, and the performance overhead of using FSR appears lower than DLSS for a given render resolution. However, DLSS 2.0 is clearly better at upscaling from lower render resolutions, such as transforming 1080p into 4K. A spatial upscaler is simply not going to be as good as a temporal upscaler that can gather information from more sources in its quest to reconstruct the image. What this means in practice is that DLSS 2.0 is much better in its balanced and performance modes compared to FSR. Where FSR can be blurry, DLSS preserves more detail. Both techniques can suffer from shimmering or similar artifacts depending on the situation. While DLSS 2.0 may be technically superior in some situations, AMD's counter for this is broader support and ease of integration. The fact that FSR works on lower end products, even those from Nvidia, is pretty neat, and really it's these cheaper products that can benefit most from upscaling technologies. A $230 GPU in normal times, like the GTX 1660 Super, is not really fast enough to run Godfall at 1440p using epic settings, but with a 33% performance boost from FSR in the ultra quality mode, that resolution becomes more of a reality without turning down any other settings. Nvidia isn't catering for this customer with DLSS, which puts us in the weird situation where AMD is doing a better job of supporting Nvidia's mainstream GPU buyers than Nvidia themselves. It will also cause all sorts of discussions at developers. With limited resources, do they integrate FSR that can cater to a wider audience but isn't quite as good as DLSS 2.0, or go for the better quality option in DLSS that's limited to RTX GPU owners? Obviously, my preferred option is to include both DLSS and FSR support. However, that may not be feasible at some studios, and even some big developers may choose the easy route here. There's a lot to play out here in the next few years, and this sort of thing appears to be AMD's strategy. With all of that said, having support for a broader range of GPUs is nice, but means little if FSR isn't actually used in games. On the balance of features, including GPU support, FSR is, in my opinion, quite competitive with DLSS. But the reality of today is that DLSS 2.0 is supported in way more games. Nvidia has had a multiple year head start to develop their DLSS ecosystem, and that's paying off now. It's all well and good to show 7 games at launch, which admittedly is better than what DLSS launched with, along with a list of upcoming titles and developers that are getting involved. But I'll be honest, the list of FSR games you can play right now doesn't get me excited. Anno is a big title, but not my sort of game and tends to be a bit more CPU limited. Godfall wasn't well received, and then there's just a few other minor games. It's not a good list right now. DLSS 2.0, on the other hand, is supported in titles like Fortnite, Call of Duty Warzone, Cyberpunk 2077, Metro Exodus Enhanced Edition, Death Stranding, and so on. Those are big games, including titles that remain popular today. Now, of course, not every game has DLSS support, but the point is that FSR isn't a selling point for AMD or non-RTX GPUs right now, just as DLSS wasn't a selling point for Nvidia when it first launched. It will take time for FSR to be supported in an adequate amount of games, whereas DLSS is miles in front and today may actually be something that will sway you across to Nvidia. Now, of course, AMD has to start somewhere, and launching in more than one game, with several more promised, and with reasonably decent technology to boot, is better than I was expecting. But really, this was needed back in January of 2020, when DLSS 2.0 is just being released, not June of 2021. That head start is massive, and it will take a lot for AMD to match Nvidia in this area. I think AMD has a promising set of tools with FSR to make up ground, but it is only a start, and I'm sure there will be more to play out. In fact, I'm certain there is more to play out based on the fact that some games like Anno list FSR as version 1.0, and speaking with AMD, they clearly have a few more things up their sleeve to improve image quality and performance in the future with this FSR technology. They're not saying a lot about what the future of FSR holds, but it does sound like there are more versions in the works down the line. So we'll see how that plays out. Anyway, that's it for this mammoth investigation into AMD's FidelityFX super resolution technology. I hope this has answered most of the questions that I think users will have going into FSR, and things like the image quality, comparisons to DLSS, comparisons to other types of image upscaling performance. I'm pretty confident that I've answered most of these things, but of course we will have a Q&A session coming up very shortly, so if you're interested and you want to ask some things about FSR and how it works, how it performs, that sort of thing, then you'll have your opportunity to do so shortly, and we will be diving into this more when we get some other interesting comparisons. In particular, I'm looking for a game that has both DLSS and FSR in it. That will be very, very interesting when that comes to play in the coming months. So yeah, that's pretty much it. This has taken a lot of time to get to this point, a lot of effort, a lot of testing, but I think that FSR is ended up being a bit of a surprise for me. As I said, I wasn't expecting it to be as good as it is, but yeah, it is kind of competitive with DLSS 2.0 at times, which, as I said, did surprise me. If you're interested in supporting all the testing that we do at Hardware Unboxed and giving us the resources to make these sorts of videos that I think we got, 4 or 5 days to make this. Normally this sort of video would take us 2 weeks on a normal schedule, so it's been not much sleep. But if you want to support us, not getting any sleep, then support our Patreon and Floatplane accounts. Links are in the description below. You get access to our Discord chat, monthly live streams, behind the scenes videos, all sorts of stuff. That's it. We're at the end. Thanks for watching. I'll catch you in the next one.